Well, welcome everybody to our little review. This is the second to last CBE, right?
Yes, the last one, well, it's the last one with new content.
Okay,
The CBE 6 is just,
a review.
yeah.
Or-
And so it's cumulative, and you also don't have to get 90% on CBE 6 to pass, by the way.
Beautiful. Oh, yeah, so we're gonna go over matrices and systems of equations, nonlinear systems of equations, partial fraction decomposition, then we're reviewing, and then also matrix arithmetic. And then we have a review question at the end, so.
By the way, my name's Caitlin.
Oh yeah, I totally forgot about that. I was like, I'm not usually the one that starts the intros. I'm Kenna. She's a recitation leader, so she knows the class really well. I'm a tutor, so I've seen a ton of different problems. But yeah, if you have any questions along the way, just like let us know, and we'll stop because we can kind of cater it to you guys since there's only 2 of you here. But
And we do record this. It will be posted on the AMLAC page. It doesn't record your faces. It only has the screen here. But if there is, for some reason, you don't want your voice recorded, still ask questions and just tell us afterwards, and we'll edit out.
Yeah.
Whatever is needed, if that's an issue.
Beautiful. Okay, so to start, we're gonna do matrices and systems of equations. So there's a couple different ways to solve systems of equations, either substitution or elimination. Basically with substitution, you set everything equal to y and then plug that in for y in one equation. Or elimination, you set them equal to each other and add the 2 equations together to eliminate a variable. And so we'll go through some examples of doing those. And then it's also important to note that systems can either be independent, which means that they only have one solution. They can be dependent, which means that they have more than one solution, or they can be inconsistent, which means that they have no solutions. It's kind of the idea of a line intersecting at one point, being parallel, or being the same line, or being parallel, that kind of thing. So for this problem, we'll solve this system of equations using elimination. And the reason that I think that that would probably be the easiest way is because we have a positive 5y and a negative 5y. So if we just add the 2 equations together, just right along right here, those are going to eliminate each other. And we'll just get rid of that variable. So we'll end up with a 2x equals 6. So then we can divide by 2 on both sides. And that gets us pretty quickly to have solved for one of the variables. After that, we can just take this variable that we found and plug it into either one of the equations, so that we can solve for y. So I'll plug it into the top one. So we'll plug in 3 for x, and you have 5y equals 5. So we have a negative 9 plus 5y equals 5. So then if we add 9 to both sides, we have that 5y equals 14. And then just to isolate y, divide by 5. Now I know that y equals 14/5. So we have our x and our y. So if we write that as a point, we just have our solution is 3 and 14/5. Yeah, beautiful. Oh.
Hey, sorry. Okay, so system of equations with matrices. So we're kind of basically doing the same thing. It's just that we're going to have usually more than 2 equations. And so we use a matrix to organize it, but that'll make more sense once we do it. But like it says here, okay, so the theorem. So if the system of equations has an augmented matrix that has a row equivalent to the augmented matrix from another system of equations, then those systems have the same solution set. Okay, so that probably sounds really weird, but what it is saying is that, okay, how do I explain? It's basically saying that if you can, so if the rows of the matrix of one system, then you can multiply the rows by some sort of other number, and they'll be the same, then the whole system is equal. Here, actually, it'll make sense when we just start doing things. So, no, this isn't related to that.
Yeah, it's basically saying that like you can put a system in a matrix and you can manipulate that matrix by like multiplying just individual rows and that kind of thing, or like subtracting one row by each other. It's basically doing the steps you do for elimination and substitution within a matrix. They're just saying that after you do all of that, it's equal to the matrix at the beginning.
Thank you.
Yeah.
You explained that so much better than I did.
That's because I had time to process what was going on while you were processing it out loud.
Yeah. Yeah. But did what Kenna say make sense? Okay. Basically, we can add and subtract rows. And it's fine. Which is basically what we were doing before. Because we took this and we multiplied by something and then we subtracted. We're doing the same thing here, it's just in a matrix. Okay. So this is the system that we originally started with. And then it's telling us this system of linear equations has the following REF, that it stands for. Reduced, thank you. I don't know what that stands for. Reduced row echelon form. Augmented matrix. So is the system independent, dependent, or inconsistent? So basically saying it's like, hey, we took this thing, we put it in a matrix, we did our row addition, subtractions, all of those things, and we came out with this. And then it wants to know whether it's independent, dependent, or inconsistent. So remember, independent means that you have some unique solution when it's linear. So that means that you're going to be able to solve this and you're going to get one specific point for, like, you're going to get one x value, one y value, and one z value. Dependent would be if you had one of these rows that was like 0. So, okay, so to answer the question, this is independent. If you because you can take this, you can substitute it in, this is going to give you z is equal to 1. Okay, so you just solve for z. Then if you take this in here, you're going to have, hey, x is equal to -1. That's what this row tells us. Sorry, this is y. Y is equal to -1. And then this first one is saying this is x. So that's x equals 1. So you have one solution where x equals 1, y equals -1, and z equals 1. An example of a dependent one.
I think that we have.
We do?
Examples, yeah. After
Sorry.
That. No, just so that you don't have to write it out.
Thank you.
We will have them.
Okay, there we go. Then, yeah. Okay, so then it wants us to use the row echelon form to solve for x, y, and z, which we just did. Because I'm impatient. So there's that.
Yeah, beautiful. So now I think basically we're going to go through, that last example was an example of when it was independent. Now I have to decide whether this one is dependent or inconsistent. And so the way that you can figure that out is this is basically saying, like she said, we can plug in, like, this is our x row or column, this is our y column, this is our z column. So if we set this up, we would have x plus 5z equals 0, y minus z equals 0, and then 0 equals 1. And so the fact that we have one of, like, our last row has all zeros equal to 1 means that it's inconsistent because it's not possible for 0 to equal 1. That's just, like, not a true statement. So that's kind of when you set up that system of equations from your reduced row echelon form. If you have something that's impossible, that means it's inconsistent. So that would be our answer on this one for that reason. Yeah. And then this is our example for when it's dependent. And the reason for that is because if you plug in your x, y, and z right here, you get x plus z equals 1. And then you have y minus 5z equals 2. And then 0 equals 0. So that checks out. We're good. This is all possible, but you only have 2 equations to solve for 3 variables. So we'll call z our independent variable, because, or like our free variable, because whatever we choose z to be, then x and y will follow based on that. So like you could choose z to be 0, or you could choose z to be 1, or like all of those kinds of things. And then you can solve for x and y. So that's why it's dependent.
So basically you're going to get a whole bunch of solutions.
Mm-hmm.
An infinite number.
Yeah. And then the way that we write those solutions is, so like it says, we're going to let z be the free variable. So z equals z. So in that case, z equals z, which is, I love how they say that. So we have y plus z, sorry, that should be an x. So x plus z equals 1. So now we just want to solve for the variables by themselves. So we already have z equals z, so now we have x equals 1 minus z. And then we do the same thing for y. We have y minus 5z equals 2. And we're going to solve for y again, just in terms of z, because it doesn't matter what z is. So y would equal 2 plus 5z. So those are your 3 equations where, depending on what you choose for z, that'll change the value of x and y. Does that make sense? Cool. Awesome. And also, there's a typo here. That should be a plus. But beautiful. Cool. Awesome.
Sweet. Okay, so now I have nonlinear systems of equation. Okay, so once again, multiple ways you can solve it, but we're basically going to be doing the same thing. Okay, so the thing with nonlinear systems of equations that can be useful sometimes is you get kind of a choice. You can solve for just like a single variable, but sometimes it's convenient. In this case, it won't be. But in some cases, it's convenient to actually, if this had been like an x squared, for example, in this one, nope, it still wouldn't have worked. Either way, sometimes it is useful to actually solve for this term x squared instead of solving for x itself and substitute into the other equation. But in this case, that's not going to be as helpful. So what we're going to do here is we're going to start with this second equation just because it happens to be easy to work with. And we're going to solve for y. And then we're going to substitute that y into this equation. And we're going to solve from there, just to give an overview. So first of all, we have 4y plus 3x equals -4. We're going to move the 3x over to the other side. So 4y equals -3x minus 4. And we're going to divide the whole thing by 4. So divide by 4, divide by 4, and we get y equals -3x minus 4 over 4. Okay, now we're going to take that, we're going to substitute it into what we had before. So we have -3y plus 4x squared minus 2x equals 3. Okay, now we're going to substitute in our y. So we get -3 times -3x minus 4 over 4 plus 4x squared minus 2x equals 3. Okay, I'm going to distribute this negative 3 in here, and we're going to end up with 9x plus 12, all of which is over 4. And I'm actually, yeah, I'll do it next step. Plus 4x squared minus 2x, and I am just going to move this 3 over here. Equals 0.
Should the
Okay.
bottom be 12 instead of 4?
No, because so we're multiplying the whole thing. We're not scaling the fraction by negative 3, we're multiplying by 3. So it's kind of like if we wrote this as negative 3 over 1. Okay.
Yeah.
But thank you. Yeah, please check my arithmetic because I do make arithmetic errors. I try to avoid them. Okay, I'm gonna split this fraction into 2 terms. So we're gonna end up with 9 over 4x plus 12 over 4 is just 3. So it's just gonna be plus 3. Plus 4x squared minus 2x minus 3 equals 0. So now we have plus 3 here, and we have minus 3 here. So those are just going to cancel and equal 0. So then we're just left with 4x squared plus 9 over 4x. Oh, I forgot. Then there's also this minus 2x. So, well, yeah. But, so 9 over 4 minus 2, all of that times x. And that's what we have, equals 0. So if we add these two together, 2 we can also think of as 4 over 4. 8 over 4. Thank you. Okay. See, I was just saying that. Anyway. Had to.
Algebra becomes a lot harder when you're trying to do it in front of other people.
It is very true. Okay. 1 over 4x equals 0. And then we can just factor an x out of here, which is going to give us x times 4x plus 1/4 equals 0. Okay, so if we take each of these, that means one of these terms has to equal 0, right? That's how our polynomial roots rule works. So if x equals 0, obviously we just have x equals 0. Or we can have 4x plus 1/4 equals 0. And then we're going to add 1/4. 4x equals negative 1. 4x equals negative 1/4. Multiplied by, sorry, not multiply, divide by 4. And we get x equals negative 1 over 16. So these are our 2x solutions. Now we need to put each of these back in over here and solve for y. So if x equals 0, then we end up with y equals negative 3 times 0, which is just 0. So which actually just leave that out. So we just end up with negative 4 over 4, which just equals negative 1. So that gives us the solution point 0, negative 1. That's one solution. Our other one, if x equals negative 1 over 16, then we're going to get y equals negative, so negative times negative 1 over 16 times negative 3, the negatives cancel. So we just end up with positive 3 over 16 minus 4 over 4. Okay, so if we do that, it ends up working out. So 4, I'm sorry, I'm writing out of space, so I'm going to do it here. but that's 16 over 16. So that's going to give us 3 minus 16 is equal to 15 over 16 divided by 4. And when we divide by 4, we can also multiply by the reciprocal, right? So that means dividing by 4 is the same as multiplying by 1/4. So that means we're going to end up with y equals 15 over 40, no, 50, 64? Yeah. 64, 15 over 64, which gives us the point negative 1 over 16 times 15, not times, with the y coordinate 16, 15 64ths. So those are two solutions. If I did, yep, that's it.
And also when you're
Oh,
on the
no, I did it
CBE,
right. I did it wrong. It should be negative 61 over 64.
oh, I think that's right here, because that would be 1.
Yeah, because that would, okay.
So there's just a little algebra thing, but on the CBE, you can plug in that answer. Like you don't have to do all the way simplified. If it's like crazy fractions, you can like plug it in as the fractions before you simplify it with the algebra in there.
Just don't make algebra mistakes like me and write
Yeah.
64 over 16 instead of.
So yeah, but whichever one you feel more comfortable with, like simplifying it or just typing in the big thing, you can do whichever one. But yeah, I'm right. Yeah. Okay. I don't want to give you false information. I haven't personally taken the CBE this year, so, but yeah. So now we have another one. In this case, it's actually set up a little bit more conveniently than the last one because we have this term right here, which is the same as this term. So we have x squared plus y squared equals 25. So we can just directly go and plug that in for this other 25 right here, or this other x squared plus y squared.
You like that on this question?
It depends. Yeah.
I feel like there's usually something that's a little bit easier to substitute. Whether it's just an x squared and you can plug in like whatever x squared equals. But I would look for that. They might have it set up where it's a little easier to substitute.
Usually what they'll have is if one of them is linear, you might, like what we had in the last one, where you had one that had a square and the other was linear. They might do whatever they want because they're like, oh, it's linear, you can just solve for y. But if they have the squared in both of them, there will be something like that, almost always. I don't want to say always because then I end up finding some problem, some students like, what about this one? And I'm like, sorry.
Sorry. But yeah, I think most of the time because they don't want to make it like wild. But yeah. So, and then in this case, it's kind of nice because we can just go in and solve for y. So we'll subtract 25. So you have 4y equals negative 12. Then divide by 4. So now we know that y equals negative 3. And then we can just go and plug that in to either of the equations. I'll plug it into the one where you only have to plug it into one y. So I'm going to plug it into the first equation. So we'll have x squared plus negative 3 squared equals 25. That means x squared plus 9 equals 25. So x squared equals 16. Beautiful. 16, which means that x is equal to positive or negative square root of 16. So it's positive or negative 4. And then when you're plugging that in, that means there were two answers when y equals negative 3. So that means you have two different points where the x coordinate is different, but the y coordinate is the same. So you have negative 4 when it was negative 3, but you also have positive 4 when y equals negative 3. So you'll have two solutions for this one. only one solution for X, but two solutions, or one solution for Y, but two solutions for X. So, yep, beautiful. So now we're doing basically a completely different topic. We're gonna do partial fraction decomposition. And so this is basically just taking a fraction that's like complicated and breaking it up into multiple fractions that are easier to work with. So when we're setting it up, there's 3 different ways that you set it up. On the CBE, do they tell you how to set it up? Or do you have to know how to do it? I feel like I've seen some problems where they like give it to you, but.
Yeah, I'm not entirely sure.
Okay. Well, the 3 different ways that you'll do it. So if it's just a normal, just like one factor, like on the denominator, you have X plus 1 or something like that. If that's one of the factors of the denominator, you'll just give it one constant on top. That'll be beautiful. If you have a quadratic factor that doesn't simplify, whoa, I don't know where that went. If you have one that doesn't simplify, like if you had X squared plus 3 minus plus 3X minus 1, I don't think that simplifies. I don't know. So like if you end up with a factor that is just a quadratic factor, you have to add a constant with an X plus a second constant. Because for every X, basically you need a constant. And if it's quadratic, you need an extra X in the numerator. And if you have something with a multiplicity bigger than 1, if it's squared, you add 1 with an exponent of 1, another one with an exponent of 2, all the way up until you have the full multiplicity. So yeah, that's kind of how it's broken down. But yeah. So these are just the steps to solving it. But we'll kind of just go through them as we're solving the examples. So the first thing we want to do is factor the denominator. So we'll leave the numerator the same for right now. The denominator can factor into X plus 5 and X plus 1. So now that we know the factors of the denominator, this is when we set up our separate fractions with different constants on top. So each of these is just a linear factor. We don't have any X squareds in there, and each of them only have a multiplicity of 1 because neither of the factors are squared. So that means both of them will just have one constant on top and then their factor on the bottom. So you'll just add those 2 fractions together. Yeah. So now our goal is to figure out what constants A and B need to be in order to make this equation true, in order to make these 2 fractions be equal to the single fraction. So what we want to do, it's what we've done before where you have to solve for A and B basically. So we need common denominators in order to be able to add the fractions together. So this one, we're going to multiply by X plus 5 on the top and bottom to give it that common denominator. And then this one, you multiply by X plus 1. And then since everything has the same denominator, all of these denominators are going to cancel out, right? So now we're left with 4X plus 16 equals A times X plus 1 plus B times X plus 5. So I'll just go ahead and multiply that out. So now I have 4X plus 16 is equal to AX plus A plus BX plus 5. So 5B, sorry. So now we want to set up a system of equations basically. And what we can, the way that we'll do that is all of the x terms can only add to other x terms. All of the constant terms can only add to other constant terms. If you had x squareds, those are the only ones that can add together. So basically what we can say is that ax plus bx has to equal 4x because it can't add to anything else. Same thing, a plus 5b has to add to 16 for the same reason. So we know that 4x has to be equal to ax plus bx, and 16 has to be equal to a plus 5b. And then once we've set up those two equations, when we divide, we can divide by x and all of them are going to cancel out. So now we have a second equation, 4 is equal to a plus b. So now we can go back and use our system of equation stuff that we've been going through in order to solve for these. So what I'm going to do is subtract the bottom one so that we can eliminate our a. So our a's would cancel out. We'd be left with 12 is equal to 4b. So that means if we divide by 4, b is going to be equal to 3. So now that we know that, we can just go back in, plug that in for b. So if we use our second equation, a is going to have to be equal to 1. Does that make sense? All those steps. There's a lot that goes into these problems. They're like wild. So then that means this is our a, this is our b. We can plug those in to the fractions that we made at the beginning. So we know that this whole thing is going to be equal to 1 over x plus 5 plus 3 over x plus 1. And so this should be our final answer right here. Beautiful. I love it when it actually works. Cool. Do you guys have any questions on that process? Cool. Awesome. This is one that's more intense because you have to use division. So
Fun. Okay, so when we do the partial fraction decomposition, one thing that is important is the exponent on the numerator has to be less than the exponent of the denominator. Because otherwise we're going to need more than constants on the numerator and it's not going to work out. So what we do in a situation like this is first we're going to use that fancy skill of polynomial long division, if anyone remembers that. Usually people hate polynomial long division, but it's useful. It's useful. So, okay, so we're going to do that first. So we're going to have on the outside x squared minus 2x minus 15. Then we have negative 4 x cubed 13x squared plus 49. And they were so kind to give us such wonderful numbers. Okay. So that's going to give us a negative 4x here. Negative 4x times x squared gives us a negative 4x cubed. We have to multiply by the whole thing. So negative 4x times 2x, it can be positive 8x squared. And then the last term is going to be positive 60x. Okay, so then we're just going to take this whole thing and subtract it. So that's going to give us, just those are just going to cancel. 13 minus 8 is 5. 5x squared. 49 minus 60 is negative 11x. And then we just keep minus 62. Okay, so now this next one, we have to multiply by 5 so that the x squared cancels. So plus 5. Then we're going to end up with 5x squared and then minus 10x. And then we have minus 60. No, minus 75. Okay. So these are just going to cancel. Sorry, this whole thing is subtracted. I should write that. So negative 11 minus negative 10. So that's like adding 10. So that's just going to give us a negative x. Then negative 62 minus negative 75. Once again, we're basically adding 75. So that's going to give us a positive 13. Okay, so this is our quotient, and this is our remainder. So that means that we can rewrite this as we're going to have our remainder, negative x plus 13, still over the same denominator, x squared minus 2x minus 15. Then we're going to add our quotient. So in this case, it starts with a negative, so it's actually going to be minus. But anyway, minus 4x plus 5. So these two expressions are equal up here. Those two are the same. Does it make sense how I got that far? Are there any questions about that? Okay. Then we're going to go on to actually writing the partial fraction. So this part is fine. We just leave that part as is. But we're going to write a partial fraction decomposition of this part. Okay, does this have different colors? I want a different color.
No, it doesn't.
There we go.
Oh my gosh.
So then we're going to have negative. I'm just going to rewrite it over here. So just the part that we're interested in. Actually, I'm going to write it lower down because we might want to come back up here. There we go. Okay, so negative x plus 13, x squared minus 2x minus 15. So we're going to factor the denominator, negative x plus 13 over x minus 7 plus 5, if I did that right.
Minus 5 plus 3.
Thank you. Where did I get 7 from? I don't even know. Sorry. It's a Friday, guys. Forgive me.
Beautiful. Here we get there.
I'm
That's why
s-
there's 2 of us.
I'm sorry.
'Cause
Thank you.
I wouldn't
Thank
have
you,
it.
Kenna.
I would be in the same place.
Okay. Okay. So we're trying to rewrite this as something of the form a over x minus 5 plus b over x plus 3. Okay. So we're going to do the same thing. We're going to multiply everything by, basically we're multiplying everything by this denominator is what we're doing. And then some of these are going to cancel. So that gives us negative x plus 13 equals, if we multiply this by this denominator, this negative x minus 5 would cancel. So we just end up with a times x plus 3. Same thing over here. We have b times this would cancel with that. So it just becomes b times x minus 5. Okay. So just to make it a bit clearer what I did there, I'm basically taking each of these and I'm multiplying them by x minus 5, x plus 5 plus 3 across the whole thing. X minus 5 minus 5, x plus 3, x minus 5, x minus 3 plus 3. And as long as I multiply everything by the same number, it should be fine. ignoring the points when the denominator is 0. So these, they're just both going to cancel. So that's how we end up with this here. In this one, the -5 cancels, the x minus 5 cancels, and in this one, the x plus 3 cancels. So that's where those came from. Yeah. So -x plus 13 equals ax plus 3a plus bx minus 5b. Then we have -x plus 13 equals, I'm combining like terms. This is how I usually think of it. Plus 3a minus 5b. Okay, so that means a plus b has to be this equal to this coefficient over here, which is -1. And then this one has to be equal to our constant. So that gives us our system of equations. -1 is equal to a plus b. And then we have 13 is equal to 3a minus 5b. Okay, so now we're going to take this top equation and we're just going to isolate one of the variables. Doesn't matter which one. Why is this an x? This is an a. Sorry, 3a. Okay, so I'm just going to choose a because why not? So we're going to have -1 minus b equals a. Okay, now we're going to take that and we're going to substitute it in down here. So that's going to give us 13 equals to 3 times -1 minus b, and then minus 5b, which I'm running out of room. So that gives us 13 is equal to, so that's going to be, I'm going to do the b's first. So -3b minus 5b is 8b, and then minus 3. So I'm combining one step because I don't have a lot of space.
Might be a -8.
Thank you.
Yep.
Okay, -8. Okay, so that takes us over. I'm going to add the 3 to both sides. So that gives us 16 equals -8b. And then -2 equals b. Okay, so that's one part of our solution. Then we're going to plug that back in over here with our -1 equals a plus b. So that means -1 equals a minus 2. And we get 1 equals a. Okay, so then we're going to take these two and we're going to substitute them. I'm just going to write it back up at the top so that it's all together. So we have, here's our a is 1. So 1 over x minus 5. And then b is -2. I'm going to pull the negative out front. So minus 2 over x plus 3. And then we still have to keep this thing. So don't forget about that. 4x plus 5. And it just stays hanging out there. Sorry, that was so long.
There's a lot to this problem. Good job. You did it right.
Thank you for all of your help.
I love it. Okay, now we're going into one more topic, which is matrix arithmetic. So basically addition and subtraction, they work pretty much the same. You just add across, like, they have to be the same size matrix if you're going to add and subtract them, and you just go like entry by entry. So the first entry, or like first row, first column, add together, second row, second column, entry, add together, that kind of thing. So you just go straight across. So that one's pretty simple. Then if you're multiplying by a scalar, so if you have a matrix and you just want to multiply by a number, each of them, you just multiply each of them by the same number. So you end up with the product of the scalar and each entry in your resulting matrix. It's kind of like you're just distributing it into every number in the matrix. Matrix multiplication is where it gets a little bit wacky. So what you're doing is you're multiplying in order to get your first entry in your product, you're going to multiply the first row by the first column. So entry 1, 1 is row 1 by column 1. So you'll multiply A times E and then B times G and add them together in our last one. So when I think about it, I think about like taking my first matrix and taking my second matrix and like going down through it. So all of the rows by all of the columns. And when you're doing that, these have to have the rows of the first matrix have to be the same size as the columns of the second matrix. So this one, it's easy because it's a 2 by 2, but if you had like a 3 by 2, this one would have to be a 2 by something. I just wrote an X instead of a 2. This one would have to be 2 by something because the columns and the rows have to match. But yeah, that could be a 2 by 3. But
Does that make sense to everyone so far?
So what do you do after the first row and the first column? What do you do after that?
Yeah, so then after that, if we're going on to, so this is entry 1, 1, column 1, row 1. I said that backwards, row 1, column 1. Then if we want to go on to row 1, column 2, we're going to go to the first row, the second column of the second matrix. So you take rows from the first matrix, columns from the second matrix. So, and then you just multiply those down. I kind of think about like just rotating the column on its side and then adding them together, or multiplying them and then adding them together. So yeah, you'll have your A times F, B times H. They come from that. So
It's kind of like wherever they intersect,
Mhm.
if that helps.
yeah, yeah,
I don't
that's a
know
good
if
way of thinking about it.
That's how it finally made sense to me.
Mhm. Yeah, this one, it's really weird, like thinking about almost like the geometry that like goes into it. But I think about the resulting matrix. If you're going, this next entry is row 2, column 1. So the entries for there are going to come from row 2 and column 1. And then you multiply those together. You kind of take this column, put it on its side, and then multiply those together and add up the products. But yeah, cool. Yeah, I feel like matrix multiplication, the best thing to do is just practice with a bunch of like 2 by 2 matrices so you can see how like everything's working together. But so which is what we're gonna do. We're just gonna practice it. So in this case, so our resulting matrix, what we're gonna do, so for our first entry, this is entry 1, 1. So that means we're taking row 1, column 1. We're going to take the first 2 entries. So we're going to do 4 times 10. Then we're going to add that to the second 2 entries, -2 times -9. And then the next one, still in row 1. Now we're going to do column 2. So we'll take that first row, that second column. So from there, we'll have 4 times 4. We'll add that to the second 2 entries, -2 and -10. And then we'll do that. Now we're going on to the second row, but the first column for entry 2, 1. We'll have -9 times 10. And we're going to add that to the second 2, which is 2 and -9. And then our last one is row 2, column 2. So I guess I didn't need to erase that. But we'll go with the second row, the second column, and then each of those entries, 9 and 4, and then the second two entries, which are 2 and -10. So then after we've lined that up, we can just simplify. So we'll have 40 plus 18, then 16 plus 20, -90 minus 18, and -36 minus 20. And then once we add those together, we'll get 58. 36, nope, 46, nope, 36. I was right the first time. -108 and -56. Yeah, theoretically. Beautiful. Does that all make sense? Any of the process that you want to go over again?
That's just the answer.
Beautiful. That's just the answer. I love it. I love that it works too. Sometimes my math doesn't. Okay.
So now so this +2 here, and this minus, we can kind of think of it as a -1. Those are just the scalar multiplication is all we're doing. So we're just gonna do them in. So this negative, we're gonna distribute it to like each entry, basically. So that's gonna give us 2, -5, -3, +5, -5, thank you. And then plus -6, 2 times 0 is still 0, 10, and 6, +6. Okay, and then we just add them entry by entry. So if we did want to, not do that. If we did want, okay, never mind. I'm not going to do that. I was going to try and change colors, but this doesn't want to change colors and I don't want to mess it up. So yeah. So if you have it entry by entry, then it'd be -12. And then that's going to be lots of circles. They're going to make it confusing. So I'm just going to stop doing that. But it's just the same entries. So that would be, nope, that is not, I multiplied. -4, that's addition. A -3 plus 10 is 7, -5 plus 6 is 1, and that's the answer, hopefully.
Beautiful.
Yes.
Cool. So the last thing we're going to do is just run through a review problem that's on the exam. And it has a similar idea to kind of what we were doing with partial fractions, where we need common denominators all around in order to be able to solve for x. So we're solving for the real number solutions, which means we're looking for the zeros of the numerators once we've simplified everything. So what we want to do is you're gonna write the answer. I'm gonna factor this denominator so that we can see what the common denominator is that we want. So that's gonna give us an x and an x minus 3, which means that we want to multiply the other ones by that so that we have a common denominator. So this one we'd want to multiply by x. This one we need to multiply by the whole thing. Times x. So this is going to end up giving us 5x squared. And again, since we have common denominators, all of them will cancel each other out. We can just focus on the numerators. And since we're looking for the solutions, it's okay to focus on that. So then we're subtracting 28. And that's going to be equal to 4x times x minus 3. And we can distribute that in. So we'll have 5x squared minus 28 is equal to 4x squared minus 12x. And then we can just take that all over to the other side so that we can start solving for x, set it all equal to 0. So that leaves us with an x squared plus 12x minus 28 equals 0. So either we can factor or do the quadratic formula. If it doesn't factor easy, off the top of my head, I think that it does, but my brain is just not telling me what the answer is. So we want it set up into 2 factors.
Maybe 14 and 2.
Oh, thank you. Would it be positive 14?
Yeah, positive 14
And negative 2. So we'd have a 14 and a minus 2. So our solutions are going to be x equals negative 14 and x equals positive 2, because that sign flips for the roots. But I love when it works. Awesome. And I think that is our last one. Do you guys have any questions about anything we went over or anything like we wanted to check on again?
Just one thing to be careful
Oh, yeah.
with these. Sorry.
No. Go for it.
Because we did have these x squared in the denominator. So if that means that x can't be equal to 0 and x can't be equal to 3. So if by some chance at the end you got a solution that was x equal to 0 or x equal to 3, you'd have to make sure to throw that out. So just keep in mind what is your denominator.
Yeah. So they can't be equal to the zeros of the denominator.
Because then you'd be